Hello, everyone, and thank you for attending today's webinar, From Hoover to Fighter Jets, a Vision and Framework for Future Aerospace Metals Processing Research. Before we begin, I would like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these during the webcast, but if a fuller answer is needed or we run out of time, you'll receive an answer later via email. We do capture all questions. A copy of today's slide deck is available in the Resource List widget, which looks like a green folder. You can expand your slide area by clicking on the Maximize icon in the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click the Help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier. Now I'd like to introduce the guest presenter for today's webinar, Dr. Eric Payton. Dr. Payton serves as the research leader for the Metallic Materials and Processing team at the Air Force Research Laboratory Materials and Manufacturing Directorate. His research focuses on the development of novel techniques for characterization and modeling of materials microstructure evolution during thermomechanical processing of metallic materials. Prior to his transition to government service in 2015, Dr. Payton was a member of the faculty at the New York State College of Ceramics at Alfred University. He held postdoctoral positions at Ruhr University in Bochum, Germany, and the Federal Institute of Materials Research and Testing in Berlin, Germany, and obtained a PhD in Material Science and Engineering from Ohio State University. Now over to Dr. Payton.
Thanks very much, Jonathan, and I'd also like to thank Stuart Wright and Matt Nowell for inviting me to give this talk and for doing all the organization work behind the scenes. Second, I want to note right away that this is not a particularly technical talk. Today I'm going to attempt to link together several seemingly disparate things while trying to convey some of the perspective that I've gained on our field in my 4 years of serving as research leader for metallic materials and processing at AFRL. And I'm going to try to present a vision and a framework for thinking about future aerospace metals processing research. And in the process, I'm hoping to inspire some of you in the audience to do research that benefits the field of metals processing. The 5 things that I'm going to try to connect are Herbert Hoover, the 31st President of the United States, a $10 big box store toaster, the ubiquitous aluminum beverage can, electron microscopy, and a $100 million fighter jet. And then I'm going to try to convince you to buy a metaphorical robotic vacuum cleaner. So the well-known futurist Sir Arthur Clarke, the author of 2001 A Space Odyssey, predicted in 1986 that the automobile of the future would be made of composites. Some of you may point out that composites actually have a long history and have been in use since the 1960s or were in use since the 1960s in the Trabi. But nevertheless, the prediction of Sir Arthur Clarke was that metal panels and metal structural materials would go the way of wood paneling, and they would be replaced by structural composites. Now, our reality now is not it's not a massive shift towards structural composites, but in fact, there's been a diversification of the types of steels. Cars are much safer and more fuel efficient than they used to be, but on average, they're not lighter. There may be, right now we may be seeing a shift towards aluminum alloys and an interest in magnesium alloys, but there really hasn't been this widespread adoption of composites for structural components. So you may be wondering, why am I talking about cars? Don't I work for the Air Force Research Lab? Well, this is an excellent question, which I'm going to try to answer in a moment. But first, I think it's necessary to go over what airframes and jet engines are made of. And they are made of metals, or mostly metals, by weight. 90% of a turbine engine is nickel superalloys, titanium alloys, and steels. More than 60% of a typical airframe is aluminum alloys, titanium alloys, and steels. So the answer to why I'm talking about cars really comes down to design philosophy. We want engineers to be able to use the right material for a given application. And a diversification of available high-performance materials really means more options for the right material for a given application. But we have a big limitation in being able to put in exactly the right material for a given application due to economics. There's the market pull for aerospace-grade materials drives costs higher. And the purchasing power of the aerospace sector and the defense aerospace sector in particular is much smaller than the automotive sector in the overall metals market. Aerospace applications, in particular require very clean grades of high-performance specialty alloys. And the health of the metals industry is important for national security. So this is why we have a metallic materials and processing team here at AFRL. And our objective in this team is to screen and reduce time to market for new alloys and metals manufacturing processes. So aerospace applications require premium quality materials. And there's this old adage that says we offer 3 kinds of services: good, cheap, and fast, but you can only pick 2. Good and cheap won't be fast, fast and good won't be cheap, cheap and fast won't be good. So for these premium quality materials, it's either going to take a long time to be made, or they will be expensive, or they could be both. So to expand the palette of alloys that we can use so that we have the right alloy for a given application, we need to commoditize, in my opinion, small batch processing of metallic materials. We need to make the good materials cheaper and faster. So what I mean by commoditization is being able to have the materials produced by different manufacturers of equivalent quality. And we think this would enable insertion of newly developed alloy compositions, reduce lead time, and increase buying power for the aerospace market. Getting there is complicated and multifaceted, but our team plays a role, and metals processing research plays a role in a part of this. So a commodity is a staple product that's price sensitive and can be made of equivalent quality by different manufacturers. So the other side of this is artisanal. So artisanal things are produced in limited quantities by an artisan through traditional methods. So you may be thinking of like cheese or bread, but artisanal can also refer to how metals are produced. And artisanal mining, as an example, produces 20% of the world's cobalt, which is a key ingredient in high-temperature alloys and batteries. So I'm making the case here that aerospace mill products are specialty materials, and that those who produce them are artisans. The nickel and titanium bar and plate products that you can buy off the shelf may look very uniform, but the process for making them is surprisingly artisanal. Many operations are still performed by hand by very experienced operators, and automation is actually limited by the quantity that's produced. And this variability, this subtle variation from piece to piece, has to be accounted for reactively by mill workers. And this variability in the process affects microstructure, which in turn affects lifing and performance. So here I'm going to show a simple lab scale example of sources of variability. And actually, We'll show a video in the next slide. I'll warn you in advance, there's a grating noise that occurs in the background. But in the video, you'll see in our lab a titanium 6.4, Ti 6.4 workpiece taken from a furnace and put into a forging press, and the tongs have produced local cooling. The temperature difference locally affects the local flow stress and results in a constriction across the diameter. Now, this is just a simple lab scale example, and in fact, there's a balance here that's played between the time from furnace to the forge press, the time on die, and the time before we hit the buttons. So if we were to hit the buttons to start the forge press a little bit earlier, then there might have been even more of a constriction here. Now, this is just a single forging step, and real aerospace forgings might have hundreds of individual steps. Differences in reheat timing and handling will accumulate, and metal retains a memory of this through variations in the microstructure. So at this point, I'm going to hit next and push the video clip to you. You will see the workpiece coming out, and you'll see the constriction and the cooled region caused by the tongs. But just as a forewarning, this is going to, there will be a grating noise for about the next 17 seconds as you hear the noise of the press. So at best, this the variability that I'm talking about. Sorry about that. Sorry about that. I accidentally hit back too many times. So the variability that I'm talking about will, at best, it will be reduced by additional processing steps. But at worst, it can produce anomalous microstructures that will really seriously impact the life of a component. So at this point, I'm going to talk a little bit about commodity materials and specialization. And I read this humorous account of attempts to make your own commodity materials last year, a book that I highly recommend. And in it, the book's called The Toaster Project by Thomas Thwaites. And in it, the author sets out trying to manufacture his own toaster from raw materials, going back to refinement of iron ore, electrolytic extraction of copper, synthesis of polypropylene, and et cetera. And Thwaites at the time was, he had bachelor's degrees in economics and biology. He found material science and engineering textbooks not useful at all for learning how to produce these common everyday materials that he needed to be able to make his own DIY toaster. But he did find one book really helpful, and that book was an English translation of a Latin text, De Re Metallica. The translator was Herbert Hoover, the 31st President of the United States. Hoover was a geologist, mining and metallurgical engineer. Fascinating guy if you go back and read about him. He was a true rags to riches story. He managed engineering projects in Australia and China, founded a successful mining consultancy firm, and he wrote what became a standard textbook at the time on the principles of mining. He used his wealth to organize refugee programs in World War I, during World War I, preventing the starvation of millions as the head of the United States Food Administration Bureau. He was the Secretary of Commerce, promoting international trade, and was influential in development of air travel. But he's not remembered for this academic work or for his translation of De Re Metallica. Actually, he's remembered for his administration's handling of the economic fallout from Black Tuesday. So back to small batch craft materials. The picture you see here is the result of the 9 months of work that are documented in the toaster project. And I want to point out this quote from Thomas Thwaites. He says, "Looking back, I'm slightly embarrassed by my naive optimism. The technical and scientific expertise assembled by countless people over centuries could not be replicated by me in the 9 months that I had available." So, after all, the technology that he was trying to replicate had existed for over 100 years, but those materials, that knowledge the scientists had stood on the shoulders of giants and brought these materials from what were specialty materials down to commodities that could be produced such that you could have a $10 toaster. So Thwaites made a toaster with limited functionality almost from scratch in 9 months for nearly $2,000. You can have a toaster with more features at any big box retail store for about $10. All this is to point out that in the real world and industry, there's building off of decades of knowledge to process materials such that they have amazing properties. As an example, for an aerospace relevant example, modern superalloy, the size of your pinky, can hold up 4 grand pianos at temperatures above the melting temperature of aluminum for 1,000 hours. That's pretty amazing. And this is done in some of these materials in kind of smaller batch processes. Now, in order to bring down costs and be able to get the right material in a given application, I'm arguing that we need to move from specialty alloys to commodities. And I want to bring here the example of the beverage can. Aluminum cans went from an impossibility to a commodity in a matter of decades. Back in the mid-1800s, aluminum was worth more than gold. And in fact, Napoleon III had a set of aluminum cutlery for his VIP guests. His non-VIP guests had to use gold cutlery. Steel cans for holding liquids under pressure were actually not even developed until the 1930s. But by the 1960s, aluminum cans were a no-brainer. They were widely available, cheaper than steel, easier to ship for lower weight, easy to recycle, imprintable with your own logo. And this commoditization happened in part because of industrial academic partnerships. Physical metallurgists studied the properties and processing of aluminum alloys, and this led to making cans easier to mass produce. Metallurgical and mining engineers developed scalable processes for extraction and recycling. And so I'm advocating for this as a proven route to transitioning specialty materials from the laboratory to application. And at AFRL, we seek out facilitating these collaborations with both academia and the metal supply chain. So microstructure control during processing is really important for cost reduction for aluminum cans. The forming operations, the ironing out of the walls, produce a very, very strong crystallographic texture, which causes earring. And controlling the strain paths in history during processing is the key to controlling the texture. Something quite similar happens, in a way, in the processing of titanium alloys. So depending on the strain path, you can end up with very strong textures forming. And when these strong textures form, in beta annealing, in a beta annealing process, you may end up with these coarse grains forming. And the coarse grains can be a fatigue crack initiation risk. So in our current research program on this particular topic, we're doing forming operations on the forging press. We're modeling this tracking the local thermomechanical processing history and trying to link this up to crystal plasticity to understand location-specific texture and subsequent microstructure evolution upon beta annealing. So beta annealed microstructures are often said to have better fatigue crack growth behavior and higher toughnesses, so that's why they're chosen for damage-tolerant applications. Now, this isn't necessarily true for all crack lengths and applications, but it's the general thinking. Coarse grains are observed in many different operations, but what ties them all together in our observation is a high fraction of that process being a plane strain condition. So the plane strain condition produces microstructures that then can lead to coarse grain formation. So this is to say that local thermomechanical processing histories matter, and so when you see the tongs cooling a certain part of a workpiece, that's going to change the microstructure in that workpiece, and we want to be able to understand and model that in each step of the process in order to make it reduce the incidence of anomalous defects as well as improve the quality of these specialty materials. So our vision is to be able to make local predictions of microstructures within a finite element framework to give us the ability to optimize processing routes for performance, to give us new starting points for including microstructure in our useful life predictions of components, and to give us a new tool for failure analysis, where we can ask, how might we have gotten this anomalous defect in a component? So parts of putting together this future modeling capability, we need more accurate input parameter calibrations. We need improved physics-based models for microstructure evolution that take into account what we know about deformation mechanisms, and we have to incorporate these into multi-physics simulations for processing. There's a role for data science in all of these areas, but data science for metals processing is quite different from the data science and machine learning that we're most familiar with from Silicon Valley. Machine learning, we all know, takes pretty large quantities of data for training. In the case of Silicon Valley, Facebook and so on, people voluntarily share their photos, creating a huge data set for training facial recognition. People tag their own metadata in their free time. For creating maps, Google drove cars through streets all over the world several times over more than 10 years collecting photos. And, those companies that are trying to work on self-driving cars, they have cameras that can run and record how the person is driving and link this up to what's seen in the video. If we compare that to our current situation in metals processing, specimens, or metals processing research, we prepare specimens by hand or in a semi-automated manner. They're typically loaded only a few at a time at max into microscopes. We take images only of a few select locations, and we down select those locations to analyze. Our volume of data isn't remotely comparable for training, and it's much more expensive to obtain. Furthermore, there's lots of metadata to capture for each image, and it is time-consuming to capture that data and associate it with each image. The bottom line is that microstructure training data is really expensive, tedious to obtain, and engineers have to spend a lot of time creating the metadata. So a number of things have been written in recent years on the impact of machine learning and AI on materials and process engineering, predicting what the future might hold. One thing that's in common in all of these, in general, is the limitations of black boxes. The black box nature, which is built into machine learning algorithms, that's, and AI, that's in a way the point of them. The black boxes limit their use in high consequence applications, things that require scientific principles and decision making. So it may limit our ability to build an autonomous research robot. That's a pretty big challenge. Further, there are limitations in accessibility and education for practitioners in using them. There are risks associated with using machine learning and coming out with the wrong conclusions, which I'll go into the humorous anecdote in just a moment. There's a case for when to use a black box and case when you shouldn't use a black box. When the cost of the wrong answer is low relative to the value of getting the correct answer, and when it produces better results, those are the cases when absolutely you should use a black box. But to find causation or develop understanding, or when we lack the knowledge, judgment, or responsibility to evaluate the costs associated with bad decisions, those are cases where we shouldn't use a black box. So 4 examples here of machine learning and the black box: a robotic vacuum cleaner, self-driving cars, voice recognition for meeting transcriptions and closed captioning, and autonomous alloy and process development. In the case of a robotic vacuum cleaner, there's low consequences of failure, training data is easy to acquire, and at best it saves you time. At worst, you still have to go back and vacuum something yourself. In contrast, self-driving cars, a failure is potentially catastrophic to human lives. It's very high risk and also very high reward. So assuming with proper training and proper handling of anomalous events, a self-driving car could actually be safer than a human driver. And as more people are texting and driving, this becomes a bigger, and the risk and reward payoff seems to be changing. Voice recognition for meeting transcription is also something where there's low consequences of failure, but it provides a lot of benefit for hearing impaired. Autonomous alloy and process development is more like self-driving cars. Failure could be very, very expensive to equipment and to work pieces that have high value. So in the robotic vacuuming example, just going into a little bit more detail, risk versus consequence payoff here. If a cat sabotages your automation run, it's just not a big deal. And, your vacuum cleaner might ingest your kid's socks, but your investment of hundreds of dollars probably saves you hundreds in recovered time. And it has this surprising positive externality that you have to keep your home picked up. In contrast to self-driving car, there's this high risk of getting the algorithm wrong, and what's wrong is driven by rare events and has very serious consequences. So another consideration with the black box is bias. And there was this audit of an algorithm that was published in the news not too long ago, where they found that a resume screening company that was using a ML algorithm found two factors to be most indicative of job performance: whether the applicant's name was Jared and whether they played high school lacrosse. So we always have to be wary of whether we're biasing our results by using one of these new tools that's available to us. So as far as applying these to metals processing research, I think we have to look for low-risk, high-reward applications. So we can start from the basic premise that the reason that we need this is because humans are flawed and computers can do things better. Then we need to question, the question that follows is, why are humans flawed? It often probably because the tasks are boring and repetitive, and humans procrastinate, and the computer might be able to do it better. Many of us in this audience have experience with the boring jobs of quantitative characterization of microstructures or sample preparation. So what we need to do is take away these boring tasks from humans and give more time and resources to give them more time and resources to answer the complex problems. So my question is, the question here is, what is your robotic vacuum and your self-driving car for sample preparation and for materials characterization? I would argue there's a lot of opportunity space here, and the low-hanging fruit, where there's low consequence of failure, high efficiency gains when we get it right, low implementation cost, and reduced burden on researchers, really is the quantitative analysis of microstructure images. I think that this is the lowest complexity and highest risk versus reward payoff. So in summary, I'm going to say that aerospace metals processing, something that I have observed, I believe that it is surprisingly artisanal. Low production volumes, it has low production volumes relative to the automotive industry. The high quality that's required really requires expertise, very good ingredients, and custom equipment, so it's not something that you can easily reproduce in your backyard. It's very hard to make high quality, in an analogy to the toaster, it's very hard to make a high quality home-built airplane. Production volumes can make the best alloys cost prohibitive, so we should be thinking in our research about how we can diversify the available alloys and commoditize the metals processes so that we can enable using the right material for a given application. And by commoditizing current specialty alloys, we create room for a new generation of specialty materials. Finally, in summary, the further basic and applied scientific research is really needed to enable affordable small batch processing of novel specialty alloys so that we get the right material for the right application. In this case, tying this back to electron microscopy, the further research that's needed, tying also to the titanium processing situation, is things like looking at large areas, EBSD scans, to get better understanding of how the texture evolves from one part of a component to another. In the case of titanium, we have to have high-quality reconstructions because we tend to look at the material in Type 6.4. We're looking at the alpha phase, but when you're in alpha-beta processing, the beta phase texture evolution really matters for subsequent development of microstructure. We need to advance quantification techniques and improve our ability to get error bars and to obtain stereological results, so infer what the 3D structure is from 2 dimensions. And we need to correlate all of this with chemistry and local changes, all with the purpose of calibrating and including deformation mechanisms into the appropriate scale models so that we can model processes and make it easier to transition new alloys into aerospace applications. So I want to conclude this with an audit of whether I've succeeded in connecting these things, these seemingly disparate things together. So if you want to do process metallurgy from scratch, you may need to go back to Hoover's translation of De Re Metallica. Otherwise, it's best to stand on the shoulders of giants from the past 150 years of metals research. So there's my Hoover connection. Commodity product like the $10 toaster really wouldn't be possible without decades of expertise in processing the materials that go into it and taking materials that were once specialty materials and are now commodities. The aluminum beverage can went from an impossibility to a no-brainer in about 30 years due to industrial academic partnerships, which are a proven method for being able to bring these specialty materials to the market. And we want to apply the same tried and true approach for understanding and pushing the limits of what's possible with nickel superalloys and titanium alloys. And we will use that knowledge to try to make modern aircraft and future aircraft possible. So finally, to accelerate this process in the future, I believe the lowest hanging fruit may be to automate the most tedious image processing and data collection tasks in electron microscopy. So I hope that I have convinced you to buy a metaphorical vacuum cleaner for future image processing and removing some of these tedious tasks. So with that, I'd like to conclude in this lecture. I hope that I've connected Herbert Hoover, a $10 toaster, beverage cans, electron microscopy, and a $100 million fighter jet. And I hope that I have motivated you to consider how you might use machine learning and automation to improve metals processing research in the future. With that, I would be happy to take your questions, and I appreciate your attention. Thank you. So first question I see is aluminum became, it's actually more of a comment, aluminum became cheaper because its derivation from nature became cheaper. That's what made it a commodity. Yes, that is partially true. That's one of the two reasons that I gave in the presentation. So you're exactly correct. So if anybody has questions, feel free to submit them, and I will be happy to answer them. So the next question that we've received is, will composites replace aluminum in the aerospace industry? This is already taking place to some extent. So I think that there are definitely applications where aluminum will be replaced by composites. So next question from Jonathan Goldstein is, how will that be replicated for specialty metals? That is a excellent question. I'm actually proposing that this is something that needs to be considered. I think the role that people with my expertise can play and is working on the processing, the solid state processing side. Next question is, do you see that AI could help with the development of new alloys? I think absolutely that it is that AI can be used to fill in the gaps, but in combination with AI, we need to have good screening metrics, and we need to have probably high throughput experimentation. The next question, can robotic systems make metallographic preparation more efficient? Absolutely. I think that is true. Yes. Next question, yes, we are, I am based, that the AFRL site that I am working at is based in Dayton, Ohio. The next question is from Sean Wallace at EDAX. what processes are the low-hanging fruit in your eyes? I need further clarification on that question. So are we talking about metals processing, or when I spoke of low-hanging fruit, I was referring to mostly characterization, time-consuming characterization tasks. Next question, Felipe Ferreira from Universität Bayreuth. How do you see the use of AI for sample preparation? Oh, that's a good question. I think that if there's a way to include a computer in the loop in looking at, say, if we have a robotic system, just for example, that could do polishing and then look at the sample surface, try to do EBSD on the surface, it could, for example, see whether you can get a pattern or not, and whether further sample preparation is needed. Next question, which do you think will be more efficient, teaching material science to a programmer or training material scientists how to code image processing techniques? I would advocate for collaborations between the two. I think in this case we may need material scientists who can speak the programming, who can speak to computer scientists, and computer scientists who can speak the language of material scientists, or at least to a sufficient extent to be able to make progress in this area. It, of course, requires patience and hard work, but I think it can be done. Next question from Anil Kumar. What will be the future of additive manufacturing, especially for aluminum? So I think that additive manufacturing plays a role in commoditization of metals processing, and it's certainly opening new avenues, but it's not the only answer that we have. So I think of additive manufacturing as being an additional tool in the toolbox for metals processing research, or metals processing in general, and therefore it is because it's another tool in the toolbox, it adds to our overall need for physical metallurgy, physical metallurgists, physical metallurgy training, and the science of metals processing. It adds to what we need rather than takes it away, because it's an additional process that we can employ to get the right material for a given application. Next question, Stephen Claves from Arconic. With so much microstructural data being generated across the country, do you see a possibility of a national effort to collate and advance material understanding to accelerate processing improvements? I think that it's a great idea, and something that that could definitely advance materials understanding and processing improvements. And there are some efforts to put data out there, but I think that a challenge comes from that a lot of data is generated by companies in industry, and so sharing some of the data is a bit challenging. So I think that there's a possibility for a national effort, but I don't know how easy it would be to apply to do such a national effort for specialty materials, for specialty alloys. And last question for now, how will specialty metals become commodities without becoming cheaper? I think that they have to become cheaper. I think that making them cheaper is part of the equation. That's onto the idea. The big picture idea here is trying to move specialty metals toward being commodities in order to make them cheaper, and in the process, I think this makes way for new specialty materials. So with that is all of the questions answered. I do really appreciate this opportunity. I'd like to thank Matt and Stu and Jonathan once again, and thank the audience for their attention.